Hello students, welcome to our quick review for the Newton's laws of motion. So we have here the Newton's first law. This states that an object at rest remains at rest and an object in motion remains in motion with the same speed and direction. So this law is also called as the law of inertia. So what is inertia, by the way? So inertia, it is the tendency to do nothing or to remain unchanged. And the first law is in the inertial frame of reference. So from the word inertial frame of reference, this is the perspective that the object is at rest or in constant velocity, and therefore the net forces is equals to 0. What does this mean? So for example, we have here a book on the table. So the book on the table is at rest, means that it is not in motion. So there is a certain force that's pulling the book downwards. So this is what we call the gravitational force, right? And also there is an opposing force that's pulling the book upwards. So this is what we call the normal force. To draw the FBD of this, so we have here the FBD or the free body diagram. So we have here the normal force and then the weight or the gravitational force. So let's say, for example, the value of the normal force of the book is 15 Newton. So it should be equals also to the weight or the gravitational force of the book, so that you can achieve an equilibrium or it can be equals to 0, which means that when we try to compute the net forces of this certain situation in the free body diagram, we have here the normal force minus the weight, because the weight is going downwards. So 15 minus 15, that is equals to 0. So this means that the object is at rest or they have balanced forces. So if they have balanced forces, the object is not moving. The book is stationary. Alright. Okay, let's go to the x-axis. So let's say, for example, this is Miss Casey. She is trying to push a certain object to the direction opposite of her. But then she can't move it because there's a certain friction that's opposing the applied force. So we have here, let's say, for example, this is Miss Casey's applied force, 20 Newton. And since the object is not moving, like it doesn't really move, so it must be that the friction force is also equivalent to the applied force of Miss Casey. How can we say that the object is not moving, man? So let's try to compute the net force of this one. So we have here the net force in the x-axis. So we have that should be equals to 0. So the applied force minus the friction force, because the friction force is the opposite force to the applied force. So that's 20 minus 20. So you have the value of 0, which means that the object really is not moving, or it is at rest. Therefore, they have balanced forces. They are in equilibrium with each other. Alright? Okay, let's try to solve a sample problem applying the first law of Newton. So we have here a 180-pound cargo is found inside a freight elevator that heads up to upward at a constant velocity. So take note of the word constant velocity. So this will still satisfy the first law of Newton. The rope of the elevator snapped, which caused it to fall. So let's determine the letter A, weight of the cargo in Newton, and B, the normal force exerted by the elevator's floor to the cargo before and after the rope broke off. So you have a certain idea on your head that the net force of this certain situation will be equals to 0 already. So whatever is the value of the weight, that should be also the value of the normal force. Alright? Okay, let's try to draw this a certain example. So let's have the free body diagram. There's a certain normal force that's pulling the object, the cargo, upwards, and there's also a certain force that's pulling it downwards. So there is no applied force, so therefore there is no friction force also. So let's solve. So we have here the balance force in the y-axis. This is along the y-axis, so that should be equals to 0, right? So the normal force is going upwards, so that is positive, and then the gravitational force is going downwards, so it should be negative. Okay, so N is equals to W, so they should be same with each other. So what is the value for W? So from our formula, weight is equals to mass times gravity, right? So we have it here. Weight is equals to mass times gravity, where the mass of the cargo is 180 pounds, okay? So since this is in pounds, we have to convert this one to kilograms, right? So we have it here, 180 pounds. Then we know that in 1 kilogram there is 2.20 pounds. So we're gonna put the pounds here in the denominator so it can be cancelled, and we also put the kilograms in the numerator. So to cancel the pounds, so we have the value of 81.82 kilograms. So this is the converted value of the 180 pounds. So we have 81.82 kilograms, and since the acceleration due to Earth's gravity, that's 9.8 meters per second square, so therefore the weight of the cargo is 801.82 Newton. So this is the value of the weight of the cargo, and since it is in equilibrium with each other, whatever is the value of the weight will also be the value of the normal force. So 801.82 Newton, that's also the normal force value. Alright, let's have the second problem. We have here a 250 metal slab needed to be moved up inside a vehicle using a smooth inclined plane. Take note, we have an inclined plane here. So with the following dimensions of the inclined plane, the length of the inclined plane is 0.8, and then the height would be 0.5 meters. So what is the magnitude of the force required to move the slab if the friction force is equals to 2 Newton? So let's draw whatever is happening here. So we have an inclined plane, right? So we have a metal slab which is 250. So there is a certain applied force that is unknown. So this is the unknown, the magnitude of the force required to move. So while there is a certain force unknown, there's also the opposing force, which is the friction. And the inclined plane has a certain dimension of, the length of the inclined plane is 0.8 meters, while the height is 0.5 meters. Okay, the friction force, by the way, is 2 Newton. Okay, that's the friction force. Okay, so let's try to put everything in a free body diagram. So we have an inclined surface, so with a certain length of 0.8 meters, and then the height is 0.5. So the friction force is 2 Newton. And then the normal force, it's always perpendicular to the surface. So our surface here is an inclined plane. So we're gonna solve for the applied force. How much is the applied force to move the slab upwards? So the normal force, and we have the weight. So notice that since this is an inclined plane, we have to twist our diagram. What do you mean by twisting the diagram? Means that the applied force will be along the x-axis, that is F applied, and then the friction force is also going to be along the x-axis, that's 2 Newton. The normal force is going to be along the y-axis, and the weight, so if you try to twist that, this is the certain y-axis of the weight, right? So the weight is here, not here, but here. Okay, so this is our free body diagram. Okay, so what's the next thing to do? Remember that since this is not, the weight is not along the x and y axis, so you have to know that there are certain components of the weight. So you have the wx and you also have the wy. So the wx is here, same direction with the friction force, and the wy is here as well, along the y-axis. Okay, what's the first thing that we will do is that we will try to get the forces along the x-axis and along the y-axis. So we will separate the net force along the x and also the net force along the y. With our revised free body diagram, we can actually solve already the net forces along the x-axis. This is equals to 0. The applied force, that's positive because it's going to the right. The wx is negative, and the f is also negative. So minus f minus wx. Okay. For the forces along the y component, we have this 0 and minus wy. So next question, how do we get the values of the weight along the x component and along the y component? So remember that the weight is equals to mass times gravity. And since the weight is a resultant vector of x and y, So we can actually solve using the initial conditions. Wy is equals to w sine theta, and the initial condition in the x component, w cosine theta. We can solve for the w, or the weight. So we have it here, mg, the mass of the object, 250 kilograms. So 250 kilograms multiplied by 9.8 meters per second square. So we have the value of the weight, which is 2,450 Newton. Okay, so this is the weight that we're gonna input here and here. But the next question is that we don't have the value of the theta. So how do we solve the theta? Looking back in our certain example, you have the length and you also have the height, which means that you can get the theta using the arctan, or the tangent. So the length of our inclined plane is 0.8, and then the height is 0.5. So to solve for the theta, you will use arctan because you have the opposite over the adjacent, because this is the hypotenuse, right? So tangent theta is equals to 0.5 over 0.8. Theta is equals to arctan 0.5 over 0.8. So you have the value of the angle, which is 32 degrees. So this means that wx, which is w cosine theta, this is equals to 2450 cosine 32 degrees. And for wy, we have w sine theta. This is also equivalent to 2450 sine 32. Okay, so you can just use these values in solving for the net forces. Okay, going back, so we can now solve for our applied force. So we will transfer or transpose the negative signs to the other side. So we have here the positive F applied, or applied force, is equals to the friction force and also the Wx. So friction force, this is given in our problem. We have the 2 Newton plus the Wx, that's 2450 cosine 32. So our applied force is 2079.72 Newton. That's along the x component. To get for the y, so the normal force is equivalent to the gravitational force. So you have 2450 sine 32 degrees. So the value of the normal force is 1298 Newton. Alright, let's go to the second law of motion, which states that an unbalanced force causes an object to accelerate. So the acceleration of the object is equals to the net force acting on it divided by the object's mass. Right, so this means that the force is equals to the mass times the acceleration. So for example, now Miss Casey is trying to push a certain object which has a mass of 20 kilograms. So let's say this is point A, point B, and then point C. Because she is trying to apply an external force which is greater than the friction force, so the applied force is greater than the friction force. So that is why the object will eventually move. So this could move from point B to C. So notice that there is a certain change in position, right? So since there is a change in position, this means that there is also a change in velocity. And if there is a change in velocity, there is acceleration. So acceleration exists. The object is moving, right? So the net force will not be equals to 0 anymore, because the object will be moving already, or the object will transfer from a certain position to another. To solve for problems using or involving the second laws of motion, we will be using the force is equals to mass times acceleration, and also the kinematic equations. If you can remember, the big four equations. The big four, which assumes that they are moving in a uniform acceleration. Right, so let's have a little recap about our big four equations. So we have here number 1, we have Vf is equals to Vi plus At. 2, we have D is equals to 1/2 Vi plus Vf multiplied by time. Okay, so the third big force, so df is equals to di plus vit plus 1/2 at squared. And the fourth one is vf squared is equals to vi squared plus 2ad. Why are we using these equations? Because since there is already an acceleration, that is why we are trying to assume that the acceleration is uniform. And to solve for problems involving uniform acceleration, we will be using these different equations. So that's why the second law is also called as law of acceleration. Right, so the standard unit for the force is in Newton, the mass is in kilograms, and the acceleration is in meters per second squared. Alright, let's try to solve this sample problem number 1. We have here a net external force of 7.5 Newton exerted upon a 4.65 kilogram object. If the object's initial velocity is 2.3 meters per second when the force is applied, so let's determine its displacement after 6 seconds. So the given here, we have the force 7.5 Newton. We also have the mass of 4.65 kilograms, and the initial velocity is 2.3 meters per second, and the time is 6 seconds. So we're gonna look for the unknown, which is displacement. First, let's try to solve the acceleration using the F is equals to ma. So F is equals to ma. So divide both sides by m, so you have a is equals to F over m. So the force is 7.5 Newton, that's a standard unit, which is okay, and the mass is 4.65 kilograms. So this means that the acceleration of the object is going to be 1.61 meters per second squared. Okay, going back to our big four equations, we have d, which is unknown, we have vi, we have a, and we have d. So we are going to use the third equation. So df is equals to di plus vit plus 1/2 at squared. So since initially the position starts from 0, so this can be cancelled. So you have vit plus 1/2 at squared. So vi is equals to 2.3 meters per second. The time is 6 seconds. 1/2 the acceleration, which was solved earlier, that's 1.61 meters per second square, and then the time would be 6 seconds square. So our position after 6 seconds is 42.78 meters. Now let's go to the second problem. We have here a wind-driven ice boat initially at rest. Okay, take note, initially at rest, therefore the initial velocity is 0. On a horizontal ice rink is pushed by the wind. So there is an external force exerted by the wind. Such that after 3.5 seconds its release, it is traveling eastward. So padung siya sa east at 20 km per hour. So that is our VF, or final velocity, after 3.5 seconds. So the boat and its rider has a combined mass of 215.50 kilograms. So let's calculate the horizontal force Fw. This means that the force of the wind exerted on the boat. Initial velocity of 0, which was at rest, it was stated earlier. The final velocity is 20 km per hour. And then the time is 3.5 seconds. The mass combined by the rider and the boat is 215.50 kilograms. So we're gonna look for the force exerted by the wind. So to solve for that, you just simply use the formula F equals ma, where mass is given already, that's 215.50 kilograms. But we don't have the value of the acceleration yet. So we're going to solve the acceleration using our kinematic equations. So we can actually use the first equation, Vf is equals to Vi plus At, because it has final velocity, that's 20 km per hour. It has also initial velocity, which is 0 at rest, the acceleration, which is unknown, and then the time, which is 3.5 seconds. Right. Notice that our final velocities unit is not in standard form. So that's why we have to convert this one to meters per second first before we solve for the acceleration. So 20 meters per hour. So we know that in 1 kilometer, we have 1000 meters, and in 1 hour we have 3600 seconds. So 1 km here is 1000 meters, so we can cancel the kilometers. So 1 hour, we also have here 3600 seconds. So cancel. So the value for final velocity in meters per second is 5.56 meters per second. Okay, so now we can solve. VF is equals to VI plus AT. Okay, to solve for the acceleration, this value is 5.56 meters per second. This is 0 since this is at rest. Acceleration unknown, and the time is 3.5 seconds. So you have A times 3.5 seconds, that's equals to 5.56 meters per second. So divide both sides by 3.5 to cancel. So you have here acceleration, which is equals to 1.59 meters per second square. Now we have the value of the acceleration. So we can compute already for the force exerted by the wind. So we have 1.59 meters per second square. So we have the force 342.65 Newton. Let's go to the Newton's third law. So this is also called as law of action-reaction. It states that the force that object A exerts on object B is the same as the force that object B exerts on object A, but is in opposite direction. So to mathematically express the third law, we have here force exerted object A on object B is equals to the opposite force exerted by object B on object A. Actually, the third law will happen in pairs. So the action is equals to the opposite reaction. Okay, for example, we have here a cup of coffee on the table. So the force exerted by the cup of coffee, so let's say this is object A and then this is object B, the table. So the force exerted of the coffee on table is equals to the force, also the negative force exerted by the table on the cup of coffee. And that's it. We can also have the statement of the third law, which is every action will always have equal and opposite reaction. So to summarize, the first law is a law of inertia, second law, that's law of acceleration, and then the third law is law of action-reaction. That's all for today. Thank you, and I hope you learned something.